Today we're going to talk about infrared spectroscopy. Spectroscopy is scary, but once you understand it, it makes sense. In organic chemistry, you're probably going to learn about 3 different types of spectroscopy. There is infrared, there is NMR, and within NMR, like 2 subtypes, you have carbon NMR and proton NMR, and then you have mass spec. Mass spec and NMR are going to give you more specific data. Infrared is just going to give us an idea of the functional groups in a molecule. And here's how it happens. So we know that we can shine visible light at electrons, and electrons get excited, and then they maybe fall down and release energy, right? But you can actually do other things if you have other types of light. So here on the left, we have a spectrum of light or other electromagnetic radiation and what it can do. And it turns out if you have infrared light, infra means below, so infrared is below red in frequency, not in wavelength. Then we can make molecules vibrate. Electrons don't get excited, but the molecules vibrate. And this vibration is going to be based on how strong of a dipole moment that you have. And we kind of have to redefine dipole moment here because in general chemistry and in the beginning of Orgo even we're taught that, okay, even if you have 2 different elements that are close together in electronegativity, like carbon and hydrogen, there's no dipole moment, there's no appreciable dipole moment. But here, when we do spectroscopy with infrared and NMR, we kind of have to redefine our notion of a dipole moment and say that if anything is even the slightest bit asymmetrical, it can be a dipole moment. It's just not going to be as big of one, but it will be a dipole moment. So IR spec, to give some more background, is measured in something called wave numbers. So that's how many wavelengths you can fit into a centimeter. And because the speed of light is a constant, we can think of how many wavelengths you fit into a certain distance as kind of similar to how many wavelengths you can fit in a certain time, and that's frequency. So wave numbers, even though it's measuring like wavelengths per centimeter, it's measuring frequency. So this is a unit of frequency, but it's not the same thing as hertz. So we have nu with a little line over it because it's kind of like nu, but it's not. And to review, nu is the variable for frequency. So you have to think of these atoms that are in a bond like they're in a spring. And so in physics, when we have a spring, I know I don't like to think about physics either, but when we have a spring in physics, we can store elastic potential energy in it, and it kind of oscillates back and forth until it reaches an equilibrium where the spring is at a point where it doesn't really have elastic potential energy anymore because it's like at its relaxed point. And this is what happens with molecular vibrations. And molecular vibrations are going to happen more with or at higher frequency with a lighter atom. So for example, if you have hydrogen or deuterium, which is the heavy isotope of hydrogen in the same molecule, like say you had water and then you had like water with deuterium instead of hydrogen, then the one with deuterium is going to vibrate at a lower frequency than the one with hydrogen. And then also you have weaker bonds versus stronger bonds. Stronger bonds vibrate at a higher frequency, and weaker bonds don't vibrate as high. And so we'll start to see that when we see specific numbers at which things vibrate. And so how does an infrared spectrometer really work? So it works like this. You have an electric field, and an electric field is basically anything that you put in it that has a charge, it's going to have a force on it. And it depends on what charge that you have. So in a dipole moment, however big or small, you have a partial positive and a partial negative. And so the partial positive is going to want to go one way in the electric field, and the partial negative is going to want to go the opposite way because it's the opposite charge. And that's going to create our stretching of our molecular spring. And you can't see my air quotes, but I'm making air quotes. So this is a diagram of how an infrared spectrometer works. And I know it looks intimidating, and I would suggest to you to like kind of get used to looking at these diagrams and not getting intimidated, because if you're taking organic chemistry as a biology or pre-medical major and you're going to take the MCAT ChemPhys section is full of stuff like this where they're going to give you a bunch of boxes and they make a diagram of some analytical machine in chemistry or physics or physical chemistry. Anyways, that tangent aside, the way that this is going to work is that in whatever spectrometer you have, you're going to have a way to split light into lots of different frequencies because we want to measure every frequency separately. And so we're going to split up light using this mirror type of mechanism, and that's going to go through our sample, and then after the sample we have a detector, and the detector is going to tell us what light we still have after it's gone through the sample. And then we get a spectrum. And then this one is called a Fourier transform. Apparently it's a lot more like energy efficient in the way that it does things, and I think it's a lot less expensive as well. And the way that it works is basically you have one mirror that stands still and one mirror that moves, and because the mirror is moving, the light that hits that one instead of the other one has traveled a different distance. And so because you get lights that have traveled all different distances, because they hit this mirror at all different points in its moving trajectory, you're going to get all different frequencies without spending your money on a very expensive prism. So actually, before I start explaining to you different frequencies, I want to show you what an infrared spectrum looks like. So please ignore the labels for now, because we're coming back to this one and then we'll talk about the labels. But this whole right side of the spectrum is called the fingerprint region. So that whole area up to like 1400, it's called the fingerprint region because, like, say I'm taking the spectrum of, I don't know, ethane, right? I'm just picking a random chemical. Then if I have a spectrum already of ethane, like a different sample, those regions are going to look exactly the same, and I can compare them and be like, yeah, that's ethane. But if I'm taking a spectrum of ethane and I've never, or not ethane, if I've taken a spectrum of a new chemical that I found in nature from like a rare beetle that spits out venom, and I put it in an infrared spectrometer to try to see what it is, and I don't have a comparison spectrum to compare it to, that fingerprint region all of a sudden means nothing. Because there's so much noise in it that we're not going to see any distinctive signals for a functional group. The rest of the spectrum, however, is useful to us. And so, for example, that thing labeled OH stretch around like 3300, that tells us there's a hydroxyl group. And then we know that about this compound. So going back to the beginning, now that we kind of have seen an IR spectrum and are curious about how do we decode this, we can look at different carbon-carbon bonds, and with the carbon-carbon bonds, again, you can see that the alkane carbon-carbon bond is not useful to us because now we know 1200 is in the fingerprint region. The carbon-carbon double bond is going to go at about 1600, and sometimes that's useful. The thing is that when we see CH stretches, you're going to see that those are a lot more useful, and so we don't really care about the carbon-carbon bonds. But then, if you have an alkyne, that's going to be useful because it's farther up on the spectrum. Generally, the higher wave number things are, the more useful they are to us because there's less stuff in that region. And so if you have an alkyne, it's going to go at about like 2200. There's also differences if you have conjugation, and conjugation is just like any two double bonds that are one carbon apart. So you have a bond, you have a single bond, and then you have a double bond. That's conjugation. And so you can see some diagrams here of conjugation, and with conjugation, that's going to make the signal lower. Yeah, I did have to check that again because these things are easy to forget. And also, you don't use carbon-carbon bonds a lot in spectroscopy. But your benzene is going to be at about 1600 centimeters, or centimeters to the negative first. And so here, this diagram is making a differentiation between our internal alkynes and terminal alkynes. So a terminal alkyne, terminal means the end. If you're terminal, you're going to die. So terminal alkyne means it's the end of the compound, is where the alkyne functional group is. And this is going to have a higher dipole moment because on one side we have a carbon group and on one side we have a hydrogen, and that's more asymmetrical than if we have carbon groups on both sides. And that's what the R's mean. They mean carbon groups. So we're going to have more of a signal if you have more of a dipole moment. So now we get into the kind of more useful stuff. The CH stretching depends on what kind of hybridization you have, and essentially that's going to mean like how you're bonding. So like sp3 is single bond, sp2 is double bond, and sp is triple bond. And we're talking about the carbon actually that is bonded to the hydrogen because hydrogens don't have hybridization. So all your CH that are sp3 hybridized are going to go just below 3000. 3000 is our differentiating mark. And usually that doesn't matter because practically every compound is going to have those. But the sp2 hybridized CH, which is going to be just above 3000, that can be useful to us because that's how we can know that we have a double bond between two carbons, probably, and we have an H that is bonded to that, so it's not fully substituted. And then the terminal alkyne, we discussed the CC bond is going to be like 2100, 2200 wave numbers, but the alkyne CH is actually going to be our really good signal of a terminal alkyne because we're going to see it at 3300. Not a lot of stuff goes past 3000. Like the alkene or the double bonded carbon CH stretch, that's going to be like right after 3000, but after like 3100, the area is pretty much empty unless you have one of a few specific things, and one of those specific things is going to be our terminal alkyne, which is going to have a characteristic like sharp little peak at 3300. So this is an example of a compound, hexane, and hexane's spectrum is very boring. Notice the absence of anything here. That's going to become important to us later. Notice the absence of anything here. Notice in particular that if we draw a line at 3000, we don't see anything immediately after it here. This is another example. This one is hex 1-ene, and so now we can see the difference. If we draw a line at 3000, sorry, my line isn't very straight. You can see a signal here, and that signal tells us that we have the ene in hexene. And then we can also see the C double bond C. But that's not as useful, at least it hasn't been as useful to me. So now let's talk about the fun things. I mentioned with our terminal alkyne that there's only a few things that go like appreciably above 3000, like even above the alkene signals. And one of those things is a terminal alkyne, which is like 3300, and it's going to be a sharp thing. The other thing is an alcohol, and an OH signal is going to be around 3300 also, and it's going to be what we call broad. And when you hear broad, it's like this is spiky, this is broad. Or more like, I guess, like this. So it's going to be smooth and broad and in an area that otherwise has nothing on the spectrum. So alcohols are very easy to detect. Carboxylic acid OH is going to be shifted a little bit back, so it's going to be like 3000 wave numbers. And for carboxylic acid, you also see the carbonyl group because it's like... So this signal here is this, and then we're going to learn right after this how to recognize a carbonyl. And so then you're going to know whether it's an alcohol or whether it's an acid. And then there's also amines. Amines are going to be spiky, and that's how you know it's an amine and not a hydroxyl group. But it's like the same area. So here's some examples. This, I believe, is the spectrum that we first looked at in the beginning when I said you can see the part that says OH. Now we know there's an alcohol. Now we know why we know, because at 3300 wave numbers, we have this broad signal, and that's going to tell us we have an alcohol. We can also see that we don't have any alkene because there's nothing like right there. And then we don't have anything here. And again, that's going to become prevalent to us in important to us in just a minute. Here's another example. This is our amine. So you can see it's kind of shorter than the alcohol signal. It's also spiky, so it's not broad. And then again, no alkene, no anything in the middle. So now we're going to look at carbonyls, and carbonyls are a very easy functional group to spot. Carbonyls are going to be around 1700. Sometimes they're shifted one way or another, depending on if it's an aldehyde or a ketone or if it's conjugated. But the carbonyl spike is going to look like that. And that's like back here when we saw like a gaping hole there, that's how you know there's no carbonyl. And so if you get a multiple choice problem with infrared spectroscopy, often like half the compounds are going to have carbonyls and half don't. And then you can narrow it down just based on that alone. That's probably the most helpful signal that you need to know, is either the OH1 or the carbonyl. If you take anything out of this video, take out that carbonyls absorb around or vibrate around 1700 wave numbers. If you have a conjugated carbonyl, which means you have a carbonyl and then you have like some type of double bond, that's going to absorb lower. Conjugation lowers things. So if you have a conjugated carbonyl, it's going to be like maybe 1650 or something. There's also some other signals that are important. So aldehydes versus ketones, very similar things. But remember, aldehyde has the hydrogen. So this hydrogen is going to absorb or vibrate, sorry. I keep thinking of like UV-vis spectroscopy. It's going to vibrate around here. This bond is going to vibrate around there. So you're going to see like two little spikes in the 2000, 2700 like region, and that's going to tell you it's an aldehyde, because ketones don't have that and acids don't have that either. So as an example, here is heptane 2-one, and you can see the ketone, here. Ketones are going to be around 1710, whereas aldehydes can be around 1725. So that's a little bit of a difference. And what's this one? It's an aldehyde. So you can see that this signal is a little farther along. It's around 1725. And then you are also going to see the aldehyde stretchies right here. What is this? This is something I actually just learned about relatively recently. It's called an overtone, and overtones just come from impurities, so they kind of look like amine spikes, but they're not. They're a little bit smaller, and they're going to happen in other compounds. And they're just kind of random impurities that happen. And so here's another spectrum. This one is a carboxylic acid. So carboxylic acid, because the OH stretches around 3000, it's going to like eclipse all the regular signals you see here. And it's going to look all weird and broad like that. And then you're also going to see the carbonyl signal. So let's try an example. What do we see in this spectrum? Pause the video if you need. Okay, I'm assuming you've either not paused it and thought of it on the spot, or you paused and came back. So what's going on here? Well, we see a signal around 1725, and so this might be an aldehyde. And then we also see these two little spikes here. That's characteristic of an aldehyde. We don't see anything right past 3000, so no carbon-carbon double bond. We don't see anything in this region. This is an overtone, so we don't care. And then, of course, we're not looking in the fingerprint region because that's not useful to us. And so all we really get out of this is that there's an aldehyde, but there's not an OH, there's not an NH. A lot of infrared spec is also what is there not. So there's no carbon-carbon double bonds, there's no NH, there's no OH, there's no terminal alkyne, but we do have an aldehyde. And that's how you read an infrared spectrum. That's basically all you can get out of it, and if you want more specifics, you gotta go to other spectroscopy techniques.